Okay, let's jump right in. We are looking at a paper called Causal World Modeling for Robot Control, and the system they've built is LingbotVA.
Right, and this one comes from the Ant Group and robotics researchers.
Hey.
It's introducing an autoregressive diffusion framework, basically a new way to unify video world modeling with actually getting a robot to do things.
And the big idea here, the one-liner, is that it gives robots the ability to, well, imagine the near future.
Exactly, to really understand the causality, the link between its actions and what it sees changing in the world.
So how does it do that? Technically, it seems to come down to two key things. The first is a mixture of transformers architecture and oboe.
Yes, and that's for handling a shared latent space. It keeps the vision tokens and the action tokens from stepping on each other's toes.
And the second part, and this feels huge for actually using this in the real world, is an asynchronous inference pipeline.
Absolutely. That pipeline is what solves the lag. It lets the robot predict its next move while it's still executing the current one. It gets rid of that classic jerky robot problem where it has to stop and think.
And the results. They're claiming it really outperforms some of the big state-of-the-art methods like Pi-Zero on benchmarks like Libero and RoboTwin.
Yeah, the performance gains are significant, especially in those really tricky long horizon tasks.
Yeah.
And when it's handling things like cloth, deformable objects, it's a very strong paper.
Okay, that's the 60-second summary. Now I want to, take a step back, because when I see words like world model and imagination in a robotics paper, my skepticism kicks in a little bit.
It's a fair reaction.
We've got these vision language action models, right? The VLAs like RT2, OpenVLA, and they work. They see an image, they output a motor command. So why do we need to complicate things? What's the actual bottleneck that LingBot-VA is trying to fix here?
That's the perfect question. And the authors have a great term for it. They call the problem representation entanglement.
Entanglement. Sounds a bit like quantum physics, but I'm guessing it's simpler than that.
Much simpler, but just as problematic for a robot. So think about how a standard VLA like RT2 works. It's a feed-forward system, fundamentally.
You put pixels in one end, you get motor commands out the other.
Precisely. It's a direct input-output map. And that's fine for simple tasks. See a red apple, move hand to red pixels.
The paper argues that's not enough.
Right, because think what you're asking that single network to do. It has to understand the visual scene, which is this huge high-dimensional data. Then it has to understand physics, gravity, friction. And on top of all that, it needs to output these very precise, low-dimensional motor commands.
So it's being a physicist, a scene interpreter, and a puppeteer, all in the same set of weights.
Exactly. And that forces it to just do pattern matching. It's not learning principles, it's memorizing. It knows what to do when the pixels look a certain way, but it has no idea why the world changes when it acts.
So if you change the lighting, or maybe the object is a little heavier than it looks,
the pattern breaks. It doesn't have a model of cause and effect. This is why you see robots, hallucinating, trying to grab something that isn't there, or pouring water long after a cup is full. It only knows the statistical link, not the physics.
Okay, but people have tried to fix this. I remember papers on models like Unisim and UVA. They were world models. They tried to predict future video. Why didn't they crack it?
They definitely made progress, but they ran into what you could call the world model gap. A lot of those models are open loop.
Open loop, so they come up with a plan and then just execute it with their eyes closed.
That's a great way to put it, yes.
Yeah.
The model generates a little video of what it thinks should happen, a dream of success, and then the robot just blindly follows the associated actions. This creates a huge reactivity gap.
Because the real world is messy. It never perfectly matches the dream.
Never. The model might dream that it perfectly grabbed a handle, so it generates the next few frames of the door opening. The robot then executes the open door motion. But in reality, its gripper slipped 2 seconds ago.
So it's just standing there miming opening a closed door.
Following its own imagination instead of reality. That's the problem.
And the paper also makes a pretty subtle point about bidirectional attention. It suggests that the way models like Sora make cool videos is actually bad for robotics. Why?
This is a really fascinating detail. Most big video models use bidirectional attention. So when they're generating a sequence, tokens in the future can influence tokens in the past. It helps smooth everything out and make it look coherent.
So it's sort of looking at the end of the movie to decide how the beginning should look.
It's cheating. From a physics perspective, anyway. It uses the future to fix the past. Great for creative work, but for a robot, time only moves in one direction. You can't use the outcome of an action to decide on the action itself. That breaks causality.
The robot isn't allowed to peek at the answer key.
Exactly. If future information leaks into the past, you're not modeling reality. You're just curve-fitting data. And that's why LingBot-VA is so insistent on being autoregressive. The present can only depend on the past.
Okay, so that really sets the stage. We need a model that doesn't entangle vision and action, and it has to be strictly causal, no time travel. So let's get into LingBot-VA. Tell me about this mixture of transformers, the MOT.
The MOT is their answer to that whole entanglement problem.
How does it work? I usually think of a mixture of experts as routing different tasks to different parts of a network.
It's a similar idea, but it's about the data type. You have this massive high-dimensional video data, and then you have these tiny low-dimensional motor commands, which are just a handful of numbers that need to be incredibly precise.
And if you just jam both of those into a standard transformer,
The video data just completely bullies the action data. The learning signal, the gradients from reconstructing the video, are so much stronger than the gradients from predicting the action. So the robot gets great at imagining the world, but terrible at moving in it.
the MOT separates those concerns then.
It does. It creates a shared latent space you can think of like a meeting room for concepts. But the heavy lifting is done by specialized expert layers. Some experts only process vision tokens. Others only process action tokens.
So the vision expert might say, I see a cylinder here, and the action expert says, got it. To grasp a cylinder, I need to apply this much force and rotate the wrist like so.
That's the intuition, yes. They handle their own business before fusing the ideas in a shared attention layer. It lets the model scale up its visual knowledge without watering down the precision required for motor control. It keeps things clean.
And all of this feeds their imagination engine. I want to drill down on this because imagination can be a pretty fluffy term. What's actually happening step by step?
It's still just predicting the next token. But the key is that a token could be part of an image or a motor command. And because it's autoregressive, it's predicting the next visual state and the next action at the same time.
So it's literally hallucinating the next frame of video.
It is. It's generating a tiny video clip of what would happen if it moved its arm in a specific way. It's running a little physics simulation in its head, one learned entirely from data. It's asking itself, if I do this, does the imagined video show the result I want?
But wait, video generation is computationally heavy. I mean, if I ask a model to generate a clip, it can take minutes. A robot needs to react in milliseconds. Isn't this approach just way too slow?
That is the classic stop and think problem. And you're right. Normally, world models are far too slow for real-time control. The robot would move, then freeze for a couple of seconds to dream up the next step, then move again. It would be jerky, unusable.
So how did they get around that? This has to be the asynchronous inference part.
That's it. And this is almost more of a systems engineering triumph than a pure AI one. They just decouple the thinking from the doing.
Walk me through that.
Okay, imagine a chef chopping vegetables. If the chef makes one cut and stops, reads the next step in the recipe, then makes another cut, dinner's going to be very late.
Right. That's synchronous.
LingBot-VA's pipeline is asynchronous. The motor controller, the robot's hand, is executing the current command at a high frequency. But in the background, on the GPU, the brain is already calculating the next world state and the next part of the plan.
So the brain is living a fraction of a second in the future while the hand is acting in the present.
You've got it. They're running in parallel. The heavy diffusion inference happens at the same time as the simple, lightweight motor execution.
But isn't there a risk there? If I'm the chef and I'm reading the next step while I'm chopping, I might not notice that the onion I'm currently cutting has a bad spot. Does the robot get detached from reality?
That's a fantastic question, and that's why they call it a closed-loop rollout. The calculation is asynchronous, but it is constantly being corrected by ground truth observations.
From the actual camera feed?
Yes. Every time the model spits out a prediction, it gets compared to what the camera is actually seeing right now. If the dream starts to diverge from reality, say the cup slipped, the very next inference step takes that new information into account. It replans.
So it's constantly correcting its dream with a dose of reality.
Constantly.
Yeah.
They also trained it with variable chunk sizes, which gives it flexibility on how far it tries to predict versus how often it needs to check back in with the real world.
Okay, let's talk about the results. The proving ground. They tested this on Libero and RoboTwin. How much better are we talking? Is this a minor improvement or something substantial?
It's really substantial. Against Pi 0, which is a very solid model, LingBot-VA shows some major performance gaps. But for me, it's not the numbers that are so impressive, it's where those gaps show up.
You mentioned a toast test earlier.
Ah, yes, the prepare toast task.
Yeah.
It sounds so simple to a person. You pick up the bread, you put it in the toaster, you press the lever.
3 steps. Simple.
For a robot, that's a long horizon task. It requires memory. And with a lot of standard VLAs, you see this kind of heartbreaking failure mode where the robot picks up the bread, it moves toward the toaster, and then it freezes. Or it drops the bread and tries to push the lever.
It forgets what it was doing.
It forgets the mission. Its immediate reactive brain sees a toaster, and the pattern it's learned is toaster means push lever. It completely forgets that the previous state was I am holding bread, which implies the next action is insert bread.
It loses the plot.
A reactive model lives only in the present. LingBot-VA lives in a causal flow. Because its world model is autoregressive, the history, the fact that it's holding bread, is baked into how it generates the current frame. It literally cannot imagine pushing the lever until it has first imagined the bread going into the slot.
That's a great way to think about it. The continuity of the video forces the continuity of the logic. The visual hallucination is its short-term memory.
That's it, exactly. It has to visualize the bread going in before it can plan the next physical step.
And the other area that really stood out was deformable objects, like folding a towel.
Deformable objects are the stuff of nightmares for robotics.
Because the physics is just so chaotic.
It's because they have, effectively, infinite degrees of freedom. A block is easy. A towel can sag, crumple, twist.
Yeah.
If you tried to write down the physics equations for a towel, you'd go crazy.
And pure pattern matching doesn't work because every single crumpled towel looks different.
Exactly. You can't just memorize move gripper to coordinate X, Y, Z, because if the towel is folded slightly differently, coordinate X is now just empty air. LingBot-VA works because it predicts the visual dynamics.
What do you mean by that?
It isn't solving any equations. It's just learned to predict that if I push this bunch of pixels here, it will visually squish into this other shape. It's seen so much video of cloth that it's learned the look of the physics.
So it's intuitive physics, the same way I know how a blanket will fall off a bed, even though I couldn't write the formula for it.
That is the perfect analogy. It's learning intuitive physics through visual prediction. And because it can predict the squish, it can control the squish.
They also mentioned pouring liquids and inserting objects.
Yes, those precise manipulation tasks. Pouring is another one of those things where timing is everything. If your system has lag while you're pouring water, you make a mess. The asynchronous pipeline really helps it keep up with those fast-moving dynamics.
There was also a claim about few-shot adaptation, an emergent property.
And that gets back to the generalizability, because the model is learning the rules of the world, the dynamics. Instead of just memorizing specific situations, it can adapt much better. You can give it a new setup it's never seen before, and it can generalize.
It understands that gravity always goes down no matter what the table looks like.
Or that solid objects don't pass through each other. It generalizes the physics, not just the pixel patterns.
So to kind of bring this all together, we're really seeing a shift from these reactive VLA models that are stimulus response to agents that have a genuine temporal understanding of their world.
We are. And it shows that these huge video generation models, the Soras of the world, aren't just for making creative content. This paper is making a strong case that video generation is actually the foundation for physical intelligence in robotics.
If you can simulate reality, you can control it.
That's the whole thesis. Simulation is the prerequisite for intelligent action in the real world.
It feels like a pretty powerful idea. It's suggesting that the world model isn't just a nice-to-have feature. It might be the absolute core of what a general-purpose robot needs.
I think it's the only path forward. You can't script every possible scenario. You have to have an agent that can imagine the consequences of its own actions in a world it's never seen before.
So I want to leave you with a final thought, something to chew on. If LingBot-VA is dreaming the future to decide what to do, if it's simulating the timeline where it burns the toast and the one where it doesn't and it picks the good one, at what point does world modeling start to look like what we call reasoning?
That's the billion-dollar question, isn't it?
I mean, in large language models, we talk about reasoning as chain of thought, but isn't simulating the physical consequences of an action the most fundamental kind of reasoning there is? You know, if I step off this cliff, I will fall. That's not just a prediction, that's common sense.
It is physical common sense. And maybe we're discovering that you don't need formal logic to get there. You just need an incredibly good video predictor and a way to connect it to your hands.
If they've managed to engineer even a sliver of that, even just inside a kitchen, well, that's both a scary and an incredibly exciting leap forward.
It's a massive leap.
We'll definitely be watching to see where this technology goes next. Thanks for listening.
Until next time.